Yeah, we're only meeting 2 more times.
That's sad.
Yeah, today and Wednesday we meet, and then on Friday we're just sort of going out with the whimper. I guess it's good we had cake early because we're not even getting together for our last class meeting, right? Oh, but I'll make up for it with the vengeance on that final exam. All right, so looks like I've got a nice stack of homework assignments here for homework 13. And then the last assignment is due on Friday. Any questions about the schedule that we're going to be following for the rest of the semester? A week from tomorrow is our final exam?
Yeah.
Wow, all right. I've got a list in my office. I guess I should have brought it today, but if you'd like to switch over to the Friday section, come with me to my office after class and I'll make a note of who's taking the exam when, if you want to make a switch. Just a reminder about course evaluations. Those are online now if you'd like to respond. We might have some time on Wednesday to pull out the computers and give you some time to do it. I'm always interested in your feedback on how certain things maybe did or didn't make sense. If you think we need another lecture for a certain topic that we covered, or if there was a part of the project you've got ideas on how to improve, I'd be very interested to hear your feedback on the course. We're going to be talking today about open channel flow design, and it's actually open channel through a man-made structure buried underground. So sanitary sewers are used for conveying wastewater from people's homes to a centralized collection location where it's treated and then discharged, usually to a stream or a river or in some cases a lake. But just like we had to worry about variability of flow when it came to delivering drinking water to homes, the same is true with the flows that go to a sanitary sewer system. And for the exact same reason is because when people are using water at a variable rate in their home, they're also generating wastewater at a variable rate going out of their home. A service connection is the pipe that goes into someone's individual residence. And normally the way the regulations work is that the service connection is owned by the homeowner. And sometimes that ownership terminates at the property line so that the wastewater utility owns from the property line to the main pipeline. In some cases, the entire service connection is the responsibility of the resident. A manhole is found periodically between the pipes, and its purpose is primarily to provide access for cleaning. Because the low flow rates that are going through the main pipelines, sediment will often accumulate at the bottom of the sanitary sewer. Sanitary obviously is a euphemism for what's really going on in the sewer. It's anything but sanitary down there, but it makes your house a lot more sanitary than it would be without a sanitary sewer. So maybe they're saying the glass is half full there and calling it a sanitary sewer. So usually water is flowing by gravity through a sewer, but if you think about if there was a place that's flat, and here's the homes in this flat area, if you're going to have the wastewater flowing by gravity, the pipe is going to be getting continually deeper and deeper and deeper. And that's not sustainable for the pipe to be 3 meters, 5 meters, 20 meters underground. You can't just infinitely go deeper and have it dump at the center of the earth. That would be great, but that's just simply that much excavation isn't reasonable. So oftentimes what they'll do is maybe have some maximum depth, say, we're only going to go 10 meters, and then there would be some sort of a vault that water accumulates in, and then it would be pumped up, and then the downward slope would continue by gravity. And so a pump station, the purpose of that is to lift wastewater to a higher elevation. Maybe it's to overcome a hill that's in between the normal flow of town. Maybe is from the mountains down towards the river, or wherever the lowest part of town is ordinarily where they put the wastewater treatment plant, but there may be intermediate hills that have to be overcome with the pump station. And so for small periods, the wastewater may be pressurized, but that's not for very long, because as it's pressurized, you can't have water going into a section that's pressurized by gravity. And so the pressurized section of a pipeline is usually very brief, and it's just to get the wastewater to a higher elevation before it can start flowing by gravity again. Because of the disruption that's caused by closing down a street in order to make a pipeline bigger, usually the sanitary sewers will be sized with future conditions in mind. So thinking, what is this neighborhood going to look like in 50 years when it's completely built out, full of residences, thinking about the population densities that may be in place at the end of the design life of the sewer system. And although a typical design life is 50 years, in reality, many sewers are much older than that. And in fact, here in Huntington, we have a sewer system that's well over 100 years in age. And it would be literally impossible for them to upgrade the system. It would completely bankrupt the city and everyone who lives in it to refurbish the entire sewer network. And so we'll just sort of be limping along, putting a patch here and trying to repair a collapsed pipeline there for the foreseeable future. There are some municipalities that have tried to refurbish their sewer networks, and most notably down in Alabama, one of the largest bankruptcies in American history, one of the largest municipal bankruptcies in U.S. history in Alabama. I think it's the county that Birmingham is in, because they spent so much money updating their sewer system that they couldn't pay for the repairs.
So what do? You got a sewer system designed for 50 years, and you know that you can't fix it later. So what are you supposed to do?
Well, it lasts longer than 50 years. You know, a concrete pipe that's put into place with good bedding, so there isn't going to be differential sedimentation. Differential sedimentation would cause a concrete pipe to crack. But as long as the pipe doesn't crack, sometimes if it starts to erode, some ingenious people have figured out a way to like inflate a liner, sort of like blowing a balloon on the inside of the pipe so that it inflates, and then if it just had small holes in it, or to try and prevent water from going out of the seams. And so there have been some different schemes to try and refurbish it as cheaply as possible, but you just really limp along. Yeah. Sometimes a pipe will crack, and they'll fix that pipe and hope that the rest lasts as long as possible. Yeah. So flow is varying over time, and it's not varying only because of people, it's also varying because of environmental factors. And by environmental factors, there's two broad categories that together are sometimes called I and I, infiltration and inflow. And infiltration is what occurs when a pipe is cracked and groundwater gets into a sewer network. And groundwater tables will rise with wet weather, and the pressure of the surrounding aquifer that's trying to get into the drainage network will increase during wet weather. It's relatively constant, not as variable as inflow anyway. Inflow refers to roof drains that are connected to the sanitary sewer, and when it purposely includes stormwater runoff, then a sanitary sewer is sometimes called a combined sewer. And that's what we have here in Huntington and a lot of parts of town, is a combined sewer where both roof drains and also street level catch basins go into the sanitary sewer, and then so does the sewage, and all of that has to be treated at the treatment plant. And the problem with that is obviously you have to pay a lot of money to treat wastewater, and increasing its volume by adding rainwater increases the cost of treatment. And you might think, well, it reduces the concentration and it sort of dilutes the pollution, and that's true, but it still is far more expensive than it is beneficial to dilute the pollution. So inflow is far more sensitive to wet weather because it's coming from people's roofs, and cracks or those holes in the manhole covers, you know, the little ventilation holes, water can get in there. And so infiltration and inflow are sort of overhead that you have to not only account for how much water is going to be purposely getting into the network, but these other accidental or illegal or undesirable flow contributions as well. And so here's a picture of water flowing into a pipe from a crack, and they have these little robotic remote control cars that will drive through the sewer and do inspections, and that would be a pretty fun job, right? The first day that you do it. Probably day 2, you wake up driving their RC car again, looking at sewers for 8 hours. Better than climbing through it anyways, which is what they used to do. Here's a picture of a roof drain connection. And so water falls onto the roof of the building, and then that pipe is just going into the ground and out of sight, out of mind, right? But no, it goes underground, and then the pipe connects to a combined sewer. And if you go through some of the older neighborhoods in Huntington, you'll see connected to people's homes, rather than discharging the water out onto the lawn, which would allow the rainwater to infiltrate, the pipe just goes underground and connects to the sewer. So there have been some efforts to try and reduce the amount of inflow, and a number of years ago, the city of Huntington actually passed a ban on it, requiring people to disconnect their roof drain connections, but it was quickly overturned when people started really complaining heavily. So right now, any old construction is grandfathered. The connections to the sanitary sewer can continue, but new construction has to allow the rainwater to discharge into people's yards, hoping that it will infiltrate to the soil. When you're trying to estimate how much water is going to be getting into sanitary sewer, it varies by location, and usually it is a government mandate, a building code, that you have to assume people are going to generate a certain amount of water. And so code-based design approach rather than reality-based design approach. And just to give an illustration of how divorced this can be from reality, people in Milwaukee apparently are going to be generating 1,000 liters per day of wastewater, whereas people in Michigan, Detroit, which is very close to Milwaukee, still 980 liters per day. But then there are some places where it's very low, like Boston. They're assuming that people will only generate 380 liters per person per day. And so it's just sort of a historical precedence from those areas. Maybe in Milwaukee and Detroit, they were trying to be very conservative and guessing how much water people are going to be generating. And you'll notice here in Milwaukee, this 1,000, you'd maybe think, well, that's how much people are going to generate and infiltration and inflow. But you notice from the comments, it says plus additional for infiltration and inflow. So it's not like they've already factored that in.
That's a ton of water.
Yeah, it is really a lot of water. 1 cubic meter of water per person. So think about a cubic meter. 1 meter by 1 meter by 1 meter. That's a lot of, it's almost a little miniature swimming pool per person per day going into the sewer network. So you can reduce the pipe sizes if you're a consultant on a big project and wanted to try and save some money. Maybe one way to do that would be to re-examine what are the assumptions for how much wastewater is being generated. I can say that here in Huntington, actually, they don't have a really ridiculously high flow generation. I think that they're assuming in the neighborhood of 300 liters per person per day. I don't remember the exact figure, but it's a reasonable quantity that's pretty close to how much water actually gets used. Since these pipelines are going to be put into places that are oftentimes not developed initially, the planning can be based on the guess of population density. And you've got some experience with planning based on population density, where you look at an area and you say, well, if it's a single-family home with relatively small lots, maybe you'd have 75 people per hectare. And then if you know how many people per hectare, you multiply that by the flow rate per person per day, and that would be a way to generate the flows that are going to need to get into the sanitary sewer. Commercial connections for businesses also are based on land use per acre and sort of code-based approaches, where there will maybe be some assumption for hospitals, some assumption for hotels, and so on. And I don't know about you, when I go to a hotel, I turn all the faucets on, because if I'm paying for that night, I want to get my money's worth. So my money's worth is 24 solid hours of every appliance turned on and all the water, flushing the toilet constantly. I hardly sleep.
All night long.
Someone use as much water as possible. And so I think that's where they come up with this 1,900 liters per day. That's because of one evening I spent in Grand Rapids, Michigan. So, industrial flows vary because a lot of factories, like a chemical factory or a food processing plant, may have its own wastewater treatment plant right there on site. And so if they have a flow equalization basin and their own treatment plant, then you really can't make the same kind of broad assumptions about a big industrial concern as you maybe could with a hotel or a residential area. And so you have to actually get a sense for who's going to be discharging to a network when it comes to industrial discharges. Infiltration and inflow. Sometimes infiltration and inflow are based on population density, or infiltration might be based on how long a sewer pipeline is, and they'll just assume that a certain cubic meters per day per kilometer of sewer line, so for infiltration. And I think previously I had, it must be in hydrology, where I've got a chart that shows infiltration at different places in the world. And infiltration in Manila, Philippines, for example, is notoriously high. About 90% of the water that flows through the sewer in Manila is actually infiltration. And so only 10% of it is legitimate sewage that should be in the pipeline, and 90% of it is because of cracks in the pipe and illegal connections. And so from place to place, you make different assumptions on how much water is going to accidentally get into the pipeline based on how much of a problem differential sedimentation is and how that may cause cracking in the pipes. And infiltration inflow sometimes is provided in liter per day per hectare. If we go back to this, you'll notice that they were saying in Shreveport plus 5,600 liters per day per hectare for infiltration. So that's an example of how infiltration is sometimes accounted for beyond the human-based uses of generated wastewater generation. And you'll also remember from the design project the idea of peaking factors, that during certain times of the day the demand is much higher than the average. You may know the average daily flow rate being generated is 300 liters per person per day. That's an average flow rate. Well, what's going to be the peak? Because that's really what you need to design for, isn't the average time of the day, but the worst time of the day. And so that varies by population. This empirical model that's shown on the left is developed under the assumption that as you have a larger population, that the peak relative to the average flow rate is going to decrease. And if you think about why that might be, if you have a really big population, that means you're going to have more variability in when people go to work, more variability in when people are awake, and also people are spread out over a longer area, and so a flush of a toilet on the far end of town takes longer to travel through the network, and so it sort of diffuses the effect of the peak. And so for a large population, a big peak, that's going to be reducing the peak ratio, the ratio of peak flow rate to the average flow rate. So that's kind of an interesting effect to think about. Now, minimum flow rates are designed so that you can have an idea of the lowest flow rate that may be going through a pipeline in order to know if the velocities are high enough to scour the sediment that can accumulate. You want to have some minimum velocity, at least once a day, to cleanse the sewer. They call it a self-cleansing velocity. Oftentimes they'll say 2 feet per second is enough to wash any solids that have settled in the bottom of the sewer pipeline. And so a minimum flow rate relative to the average flow rate is also, this empirical expression says, is a function of the population. And so a larger population is going to have an increase the ratio of the minimum flow rate to the average flow rate. So the worst case scenario is a small population because people's behavior is more uniform in a small population. Well, let's just try this out. We've got a 17.5 hectare condo development So condominiums, and we assume that the water use is 350 liters per person per day. So let's get a sense for how these peaking factors work with this example and generate the peak and the minimum wastewater flow rates. If we find the population of this area, we'll assume a density of 125 people per hectare. And so that gives us 2,187.5 people. The 0.5 people being, of course, a WVU fan. Yeah. So we get 765 cubic meters per day is the average flow rate. That's 31.9 cubic meters per hour. So if we find the peak flow rate during the day using 2.1875, so the population in thousands per peak, then we get 3655 cubic meters per day. Just by comparison, that's 152.3 cubic meters per hour. And so that's 5 times the average flow rate. And then the minimum flow rate we get is 173 cubic meters per day. On an hourly basis, that's 7.2 cubic meters per hour. And so of the average, that's less than a third, less than a quarter of the average. So wastewater flow rates vary quite considerably. And if we had a bigger population, then what we would have found is that the maximum and the minimum wouldn't be quite so far away on a percentage basis from the average. All right, pipe hydraulics. Now we've looked at partially full pipes before, right? See, I get it confused in my mind because we've got 2 sections, and I just want to make sure that we've talked about how, yeah, we've done it. It's kind of a little bit nasty, obviously, because what we have to do is keep track of the angle in radians that the water surface makes with the center of the pipe. And so you'll notice that theta here, measured in radians, is talking about the angle that's made from the edge of the water surface on either side and the center of the pipe. So if we know the flow depth, H, then from that we're able to calculate the angle that's made. And sometimes we don't know what the flow depth will be, though. And so in order to find what the flow depth is, we've combined all the partially full pipe hydraulic area, wetted perimeter type formulas into Manning's equation. And this is Manning's equation with the depth being as a function of the angle in radians. So we'll take a look at an example here in a moment to find out what the flow depth is, because almost always the pipe isn't going to be flowing full. If we design the pipe to be at capacity in year 50 of our 50-year design life, at the end of it on the peak flow day of the year, at the peak hour, then hardly ever will that pipe actually be full. That's the way it's supposed to work. In practice, unfortunately, pipes flow full more often than that, largely because as the pipe cracks, then there's more infiltration and inflow than was anticipated, and sewage gets into people's basements. That's one of the common side effects of a pipe flowing full that isn't supposed to, is the pipe becomes what they call surcharged or pressurized. And some people have a one-way flow valve as the lateral goes to the sewer from their home, and that's a really good idea, to put in a one-way check valve so that sewage can go out of your house but not come back in, because when the pipe is pressurized, then it can flood people's basements. And that was actually the subject of the research project that the hydrology students did in the fall semester this year. It was kind of an interesting approach, but most of the time the pipe isn't supposed to be flowing at full capacity. And even here in Huntington, when the pipes do fail, it'll only fail maybe once every 3 or 4 years, which is, 1 day out of 1,000 that the pipe is flowing full. Of course, 1 day out of 1,000 sounds like a lot if you're the person who's having to clean sewage out of your basement once every 3 or 4 years. So, the design procedure to find out how big the pipe should be, if that's the question, what size diameter is needed, well, you can rearrange Manning's equation to solve in terms of D, the diameter that's required. And of course, Manning's equation differs if we're working in traditional or SI units. And so this factor here that's X, that is either 1 or 1.49, depending on what units we're in. And so if you find out the diameter that's required, then you have to actually round up to the next available pipe diameter. So if you were solving for diameter and you found that a 17-inch pipe is needed, well, since that doesn't exist, what you'd do is you'd look on a table of available pipe diameter to see that 18-inch pipes are available, and so that's the size that you'd actually make the pipe. And then to find the normal depth at the maximum flow rate, you could iteratively solve Manning's equation, solve for the right-hand side. These are all knowns and fixed, the end value of the pipe, the flow rate that there's going to be, the slope, and then you would guess the angle theta in order to find the area and hydraulic radius that are corresponding to that. And when you finally find the angle that matches the two sides of Manning's equation, then you can put that angle into the formula that allows us to find the depth, the flow depth for a certain diameter as a function of the angle. So that's the approach that we're going to go through in this next example that we work. That's though just the flow depth at the max flow rate, and like I mentioned before, because sediment can fall out of the flow if the velocity is too low, we sometimes also want to find out what's happening to the water inside the pipe at the low flow rate. And so if you put the minimum flow rate into Manning's equation and find out what the flow rate is, the depth, the cross-sectional area, you can find the velocity at the minimum flow rate. And a rule of thumb is that the velocity should be above 2 feet per second or else sedimentation will occur. And, well, if sedimentation occurs during just the low flow period each day, then you can maybe assume that during the higher flow periods it will be then scoured away. But if the minimum velocity falls below 2 feet per second for several days at a time, then that sediment can sort of harden and thicken, and then it wouldn't necessarily scour.
Dr. White, on the previous slide, that one formula theta equals 2A cosine, is that arc cosine or is it the A factor area?
It's arc cosine.
Oh, okay.
Yeah.
Just wanted to make sure.
Yep, glad you asked.
Thank you.
This is what a clean sewer looks like, and then a pipe that had sediment accumulate in it. And obviously, its flow capacity is going to decrease considerably when you've got grease and grit and other solids that have accumulated in the pipe. Sometimes when we're working with flow that's only partially filling a pipe, a hydraulic element graph can be useful. And a graph like this allows you to solve Manning's equation and find out what the depth of flow is and the area and the velocity. The way it works is if you knew that a pipe, for example, is 50% full, so that its flow depth relative to the diameter is 0.5, then you can go over and find out that its discharge, for example, Q relative to Q full, down here on the bottom axis is all these other factors. So if we go to this discharge, the dashed line is if it's a N value is constant with depth, solid line N value is variable with depth. So if we assume that the N value is constant with depth, then for a half full pipe, it would show that you're getting half the capacity. But in reality, the pipe has not quite as much discharge because it's variable. The end value is variable with depth, and so you'd see that it's about 40% of its flow capacity when it's half full. And we've talked about how as it gets deeper, actually your peak capacity is when you are less than one all the way full. We've looked at these tables before because we observed how the flow capacity is actually down here greater than 1 when it's not all the way full. 100% of capacity when it's full, but being a little bit less than full means you've gotten rid of some of that resistance due to the increased wetted perimeter. And so we've seen these graphs before. One of the other concerns besides sediment accumulating inside of the sewer is that there is a toxic gas that can be formed due to sulfur in the wastewater. And in the absence of oxygen, sulfur decomposes into something that's called hydrogen sulfide, H2S. And hydrogen sulfide is corrosive. It forms sulfuric acid inside of a pipe network, and so it can erode the reinforcing steel that's in a concrete pipe. But in terms of danger to people, it's poisonous, and concentrations as low as 300 parts per million can kill a person. And compounding its danger is the fact that although it smells when you first come into contact with it, over time your nose will become desensitized. And so maybe if a worker was down underground working on pipes and smelled something bad at first, but then it went away, they'd think that, oh, it must have vented out and I'm safe now, but really it could just be that they've lost their sensitivity to smelling hydrogen sulfide. So people who work underground in wastewater treatment type jobs have to often carry with them hydrogen sulfide detectors that, on their person that will buzz at them if it's detected, because it's really dangerous. And so it forms when the water is moving too slowly, when there's not proper aeration of the flow. And so sluggish moving water or water that's very warm can promote the formation of hydrogen sulfide. It's generated by bacteria under anaerobic conditions, meaning in the absence of oxygen. And there is this empirical equation that's been developed to estimate the potential for generated hydrogen sulfide. And effective BOD is talking about the concentration of the wastewater as a function of the temperature. And so if you have a certain concentration of waste in the wastewater, then that's dangerous. But if you've got warm temperatures, then that's even more dangerous because it makes the bacteria that generate hydrogen sulfide more active. And so you'll notice that this formula that converts BOD, which is biochemical oxygen demand, into effective BOD is a function of temperature. And so any temperature above 20 degrees is going to increase the activity of the bacteria that form BOD. But the potential to generate hydrogen sulfide is lower when you've got fast-moving water. And so a big flow rate or a steep slope, either of those things is going to decrease the potential for BOD to turn into hydrogen sulfide. And so hydrogen sulfide is most of a risk during low flow conditions, when it's warm, and if a pipe is overly sized. If you've got a really big pipe and hardly any flow going through it, then that is going to possibly lead to the formation of this dangerous, toxic hydrogen sulfide gas. And so according to this empirical scale that's been generated, if you calculate Z and it's less than 5,000, then it's rare to have hydrogen sulfide formed. Above 10,000, it's likely, and in between, it's sort of just possible that hydrogen sulfide could form. All right. Well, we're going to get started on this example. I don't know if we'll make it all the way through today. In fact, when we get together on Wednesday, we might break out the tablets to go through the process of solving Manning's equation for a partially full pipe. But let's just consider what's happening here. We've got a relatively large pipe. It's about 2 feet in diameter. So the 750 millimeter diameter concrete pipe, and it's carrying a flow rate of 0.92 cubic meters per second of wastewater at 33 degrees Celsius. So that's warm wastewater. That's probably in a hot environment during the summertime months that wastewater would be that warm. And the slope is known as 0.8%. So the parameters that we're going to have to know, not only to calculate the flow depth, but also to calculate the potential for hydrogen sulfide formation, include the wetted perimeter and the parameter B, which is the function of the flow depth and the top width, B. So we'll start off by using Manning's equation, theta to the negative 2/3 power, theta minus sine of theta, the 5/3 power, minus 20.16 n cubed d to the negative 8/3 power, slope to the negative 1/2 power is equal to 0. All right, so we've got an n value of 0.013, a slope of 0.008, and a diameter of 0.75 meters. If we substitute all of that into this Manning's equation, then we're going to get that the angle is 4.23 radians. And that's what we'll actually confirm for ourselves next time. This time we're just going to go forward with calculating the hydrogen sulfide probability. Next time we'll sort of revisit the hydraulics of the situation and confirm for ourselves that we're able to calculate that angle. Okay, and so remember what that means is that this is going to be more than half full, because half full would be pi radians, or 3.14. So here, where it's 4.23 radians, we know that under the flow conditions that are described, the pipe is more than half full, but it's not completely full, because if it was completely full, that would be 2 pi radians, and so 6.28 would be all the way full. So this is somewhere in between. Okay, we can find out, for example, the wetted perimeter. It's going to be the pipe diameter times the angle divided by 2. So pipe diameter 0.75 meters, 4.23 radians divided by 2. So that tells us that the wetted perimeter of 1.586 meters, and that's what we're going to have to put into the formula for Z a little bit later, the wetted perimeter. We also want to know the top width B, and that is the diameter sine of theta divided by 2. Now H. This is D divided by 2, 1 minus cosine of theta divided by 2. And so we're going to start with the diameter divided by 2. In other words, the height of the water, or the depth, y. We find that the water depth is 0.569 meters. out of the 0.75 meters. So it's a little bit more than 2/3 full. Okay, now that we know the water depth, we can find the effective BOD. Okay, this wastewater has a BOD of 350 milligrams per liter, and that's a pretty typical concentration of BOD in wastewater. Strictly defined, what BOD just means is any pollutant that's going to cause the demand of oxygen in a receiving body. And so if you poured sugar into the Ohio River, what that would do is there would be bacteria in the Ohio River who would start eating that sugar, and there's nothing wrong with that, except for that then those bacteria would start also using oxygen that's in the river. And so they would be depleting oxygen that's required by fish. And so it's strange, but one of the worst pollutants we can put into a river is anything that bacteria are going to consume and then also demand oxygen as they consume it. And so BOD, that's biochemical oxygen demand. It means that there's something in the wastewater that is causing the demand of oxygen. And so if we put in a liter of this wastewater, there's enough sugars or carbohydrates or some sort of substrate for bacteria that they would require 350 milligrams of oxygen to break it down. So that's actually the pollutant we're talking about. The effective BOD is going to be the BOD itself, 350 milligrams per liter, and then correcting for temperature, because the rest of that equation for Z potential, that's calibrated at a temperature of 20 degrees. Since our temperature is 33 minus 20, so the effective BOD is 843 milligrams per liter.
What's the subscript 5 mean for that BOD?
Oh, that means that's how much oxygen the bacteria would require in 5 days. Given a little bit more time, they might require even more oxygen. So BOD is usually tested in a 3-day test window or a 5-day test window in the lab. They'll take a sample of water and see how much oxygen is required from it. So the 5 means 5 days. Good question. So now when we finally put it into our formula for the Z, which is the potential for the formation of hydrogen sulfide, 0.308 times 843 milligrams per liter. And then we put in the slope, 0.008 to the 1/2 power. Our flow rate, 0.92 cubic meters per second to the 1/3 power. And then the ratio, the geometric parameters, 1.586, which was our wetted perimeter relative to the top width of 0.642 meters, just the top width. Then that gives us a Z of 7373, and that's in the middle range. Greater than 5,000, under which BOD isn't going to cause the formation of hydrogen sulfide. Below the 10,000 that it's likely, so maybe H2S forms.
Is that because it's so warm?
Yes, it's because it's warm. But if the pipe was steeper, it probably wouldn't form, because the water, if the water is moving quicker, then it stirs up all that sewage and it helps to keep it aerated more. Stagnant water, warm, stagnant water with BOD in it, is that what's going to cause hydrogen sulfide to form. But if it's moving swiftly and has a lower concentration of the pollutants, then it probably won't form hydrogen sulfide. So, What's that?
So we're doing that pipe right there.
Yeah, we're probably not in any trouble at all. You can see that's rapids. Yeah, we're gonna be all right there. Exactly. We'll pick this back up on Wednesday. We'll talk more about open channel flow in the sanitary sewer, so I will see you then.